Again, welcome to Calculus. In these lectures, we are going to discuss limits. So our main objective is to find the limit of a function, both graphically and numerically. Also to understand the definition of the limit of a function, and also using the properties of limit to evaluate limits of a function. Also, we're going to use different techniques to evaluate limits of a function. So first, we start with the definition of the limit of a function and also the properties. So the definition of a limit of a function, here we say that if f at x becomes very close to a single number L as s approaches c from either side, then we have a limit as s approaches c, f at s equal to L. Again, which is read as the limit of f at s as s approaches c is L. So many times the limit of f at s as s approaches c is simply f at x. Whenever the limit of f at s as s approaches c is given as the following: limit f at s as s approaches c always equal to f at c. Also, the limit can be evaluated by direct substitution if this condition exists. So it's very important that we learn to recognize the type of function that have this property. So some basic ones are given the following list. So let b and c be a real numbers, and let n be a positive integer. So here first we say limit as s approaches c, b is equal to b. And also limit s as s approaches c is equal to c. And then limit s to the power n as s approaches c is equal to c to the power n. And also limit square root n x as s approaches c will be n square root of c. And then the property 4, we said that if n is even, then c must be positive. We know that the square root of an even number such as -2 is undefined, but -3 is okay. So these are the properties of limits. The first property is the scalar multiple. Here we assuming f at x equal to L and also g at x equal to k, as both s approaches, the limit of both s approaches c. So here if I have a limit b times f at x as s approaches c, the answer will be b times L, because f at s is L. So we multiply b. B is a value, so we multiply b by L. Also, the sum or difference, if we have a limit f at x plus or minus g at x as s approaches c, we know that f at s is L, g at s is k. So we had both L plus or minus k. Also, we have the product rule. If we have two limits, f at s multiplied by g at x as s approaches c, then we multiply the two, so it will be L times k. Also quotient, f at x divided by g at s as the limit approaches c, s approaches c, it will be L divided by k, provided k is not equal to 0. If k is equal to 0, then the limit does not exist, undefined. Also, if we have a limit f at s raised to the power n as s approaches c, then the answer will be L to the power n, because f at s is L. And also in the radical, we say limit root n f at x as s approaches c. The answer will be root n L. So in property C, as we 6, as we said, if n is even, then L must be a positive value. If it's negative, then it's undefined. So now we are going to see some few examples apply the limit properties. This will be the sum and difference limit properties. We have limit s approaches to s squared plus 2s minus 3. So we can break it into 3, saying that the limit s approaches to s squared plus the limit s approaches to 2x minus the limit s approaches to 3. So that's what we have here. Limit s approaches to s squared plus limit s approaches to 2s minus limit s approaches to 3. And anywhere we see x, we are going to substitute with 2. And so here we get 2 square, because s square will be 2 square, then 2 times limit s approaches to x, so it will be 2 times 2. Minus 3, this is a constant value. So again, our answer will be 2s, then 2 square, plus 2 times 2 minus 3. And that will give us 5. So the whole concept here is that anywhere we see x, we substitute with the 2 since the limit approaches 2. So we get 2 squared plus 2 times 2 minus 3. Now the limit of a polynomial function can also be evaluated by direct substitution. So if p is a polynomial function and c is any real number, then the limit s approaches c, p at x is equal to p at c. So we substitute c value to other x's. Now, techniques for evaluating limits. The first, we are going to find the limit s approaches 1, s cubed minus 1 over s minus 1. Now, sometimes if we have an expression in this form and we substitute 1 to the x, we are going to get 1 minus 1 divided 1 minus 1. And the answer will be 0 divided by 0. Anytime you substitute a limit value to a function and your answer is 0 by 0, it means we can reduce the expression. So in this case, we have s cubed minus 1 is the same as writing s cubed minus 1 cubed. So we can reduce it. And we know that s cubed minus 1 is the same as s minus 1 times s squared plus x plus 1. So here, s minus 1 will cancel s minus 1. And our final answer will be s squared plus s plus 1. So now we can find the limit. Anywhere we see s, we are going to substitute with 1 because the limit s approaches 1. So we get 1 squared plus 1 plus 1. So our answer will be 3. Now let's look at another example. Find the limit of the following. Here we have a square root of s plus 1 minus 1 over x. So this is a radical equation. And remember, solving this equation is better to remove the radical sign or the square root sign from the denominator. So our previous question, we used factorization formula. This section also the same thing. We were trying to change the numerator into difference of 2 squares. So we are going to multiply. We are going to multiply square root of s plus 1 divided by square root of s plus 1 plus 1. And we divide the same value and we multiply with the same value. The expression is balanced. Then the goal here is to remove the radical sign at the numerator. So here we get s plus 1 minus 1, which will give us x over x square root of s plus 1 plus 1. The x will cancel. So later we get 1 over square root of s plus 1 plus 1, as far as s is not equal to 0. So from here, we can solve our equation now. So square root of s plus 1 minus 1 over x, as s approaches 0, if we put the expression and the substitute 0 to the x's here, we are going to get a value divided by 0, which means it doesn't exist. The limit does not exist. So the best way to solve it is to, again, solve the equation first. And this is what to get. Now, if we substitute the 0, we'll get half, because square root of 0 plus 1 plus 1. So we get square root of 1 is 1. So we get half. So our answer will be again half. Now we also have a one-sided limit. And so in the previous example, we saw that one way in which a limit can fail to exist is when a function approaches a different value from the left of C than it approaches from the right of a C. So this type of behavior, again, can be described more concisely with the concept of one-sided limit. So we have f at x as s approaches C negative equal to L, or limit f at s as s approaches C positive equal. And the C positive means the limit is from right, and the negative means the limit is from the left. So the first of these two limits is read as the limit of f at s as s approaches C from the left is L. When it's negative, it's from the left. Then the second is read as the limit of f at s as s approaches C from the right. From the right means the C positive. So now we have an example here. They say we should find the limit as s approaches 0 from the left, and the limit as s approaches 0 from the right for the function f at x absolute 2x over x. So from the graph, if we plot this, we get an horizontal line at 2 when y is 2. But when x is 0, we have no existing value because we're going to have 0 over 0. So that's why we have the open period. So from the graph of f shown in the figure, we can see that f at s is equal to negative 2 for all s less than 0. Always. So that's why we have the horizontal lines. So since we know from the left, we have 2x over x. Remember, from the left means negative. So this our s can be any negative value. So the answer will be negative 2. Now from the right, s have to be a positive value. So the answer will be positive 2. So in example 5, we know that the function approaches different limits from the left and also from the right. So in such cases, we can say that the limit of f at s as s approaches C does not exist. And also for the limit of a function to exist as s approaches C, again, both-sided limit must exist and must be equal. So that's the definition for existence of a limit. If f is a function and C and L are real numbers, then the limit f at x as s approaches C is equal to L, if and only if both the left and right limits are equal to L. So here we have a question saying an overnight delivery service charges $18 for the first pound and $2 for each additional pound. Now we say let S represent the weight of a parcel and let F at S represent the shipping cost. So this is F at S. We know if it's $18 for the first pound and $2 for additional. So the first pound, second pound 20, third pound 22. So this means that we need to show that the limit f at s as s approaching 2 does not exist. And the graph of f is shown in the figure 1.58. We can see how the two differences. So when it's 1, from 0 to less than or equal to 1 is 18. And from less than 1 to greater than 1 to less than or equal to 2 is 20. Then from greater than 2 and less than or equal to 3 is 22. So again, based on this question, we have 18 from 0 to 1. When it's 20, greater than 1 to less than or equal to 2. When it's 22, greater than 2 or less than or equal to 3. Now they say we should show that the limit of f at s as s approaches 2 does not exist. So here when we plot the graph, we can see that the limit of f at s as s approaches 2 from the left is limit 2 as limit f at s as s approaches 2 equal to 20. Whereas the limit f at s as s approaches 2 from the right is 22. As we can see the values from the graph. So this means the limit does not exist. Because these one-sided limits are not equal, the limit of f at s as s approaches 2 does not exist. So that will be the conclusion of our lectures. Again, these lectures we focus on limit. We saw the definitions and the properties. And again, we're going to see more examples in our future lectures. So wish everybody the best and take care.